I'd like to start by thanking the organizer for this great workshop with very nice talks and discussion. And I would like to discuss today quantum algorithms for evolving open dynamics on a quantum computer. And before going directly to this topic, since here we are discussing problems in chemistry that can benefit from this revolution of quantum information, the quantum computing, just allow me briefly to mention the different topics. If there is interest, I would be more than happy to discuss the details of this project after my talk or later. And the first one, maybe I just mentioned this in the discussion, we're trying to use a restricted Boltzmann machine for electronic structure calculations. And we did it for finite system like molecular system, and now we're putting boundary condition to go for extended system with these restricted Boltzmann machines. The other topic has to do with quantum machine learning for state classification, and mainly we are looking at quantum phase transitions and how you distinguish between different phases if you have limited access to experimental states. And of course, the main topic will be open quantum dynamics. And then we have also a project on quantum coherence. Can, for example, quantum coherence enhance the efficiency of solar cells? Can we take advantage of quantum coherence for control? And then the next project has to do with entanglement and chemical reaction. And we are struggling for this for a while. And the idea, can we use entanglement in the reactant to control the outcome in chemical reactions? And the basic idea, like if we deal with entanglement between electrons, when you have scattering and you have output of this chemical reaction, these electrons, they're still talking to each other, and maybe we can take advantage of entanglement to control the outcome of chemical reactions. We have initial results, and I think it indicates that maybe one can use this idea to control the outcome of chemical reactions. And the last one has to do with the finite size scaling and quantum phase transitions. I mean, it looks like around maybe now 20 years ago, we developed this finite size scaling in Hilbert space. So what is the basic idea? The basic idea that you take the size of Hilbert space to be mapped into the thermodynamic limit. The idea when we talk about criticality and phase transition, you have to go to the thermodynamic limit to get the exact or true criticality and talk about the critical point and critical exponents. And since we're doing the calculation of finite size, for us, finite size was equivalent in our Hamiltonian calculation to finite number of basis functions. And now we have seen how to map basis function into qubit space. And now we're trying to see, can we do quantum phase transition using finite size scaling in qubit space and run it on a quantum computer? And we can see from initial results that one can map the size of Hilbert space into the qubit space, and you can use it to detect criticality and critical exponents. And maybe the last one has to do with the quantum games for education. And in the group, we use these kind of quantum games like the tic-tac-toe, which means you have two moves at the same time to educate or explain what is superposition, what is entanglement. We started with high school students, and then we move it to first year here students at Purdue. So anyway, I will focus on quantum dynamics, but again, if there is interest of any of these topics, I would be more than happy to discuss it. And I would like to give credit to the PhD students here in the group and the postdocs. And for us, this is really an exciting time where we start seeing students from computer science, physics, electrical and computer engineering, and chemistry joining this effort of trying to really attack these kind of problems with the new approach of quantum information and quantum computing. So here I would like to outline what I'm going to do in this talk. And for this audience, I didn't want to spend time on motivation, why the open dynamics is an important problem, but the question, how do you run it on quantum computing devices? And of course, the starting point for this is the quantum master equation. And I will show in a minute the exact form. So there's a different complexity of how do you start with a quantum master equation for the dynamics of the system interacting with the general or the complex path. Maybe the simplest approach for our discussion today is the Lindblad formalism, which is an approximation. It's a weak coupling with the Lindblad-Born approximation. I will go through the details in a minute. But probably this is an approximation, and this is the simplest one we can show at this moment. So what I'm going to do, I'm going to map it into Krauss sum operators, which is another form of writing this quantum master equation within these approximation. Why are we going to Krauss sum operators? Because these are non-unitary operators, but they can be dilated into larger Hilbert space and make it these operators unitary. And once you make it unitary, then you can see the connection with the quantum circuit and quantum gates, because these are unitary matrices. So the summary, we start with the Lindblad operator, we map it to Krauss, we take Krauss, dilate it in a larger Hilbert space, make it unitary, and then we run it on a quantum computer, which means you have to decompose these unitary operators into sequence of quantum gates. And as a textbook problem, or just for warm-up, I will show how this works for spontaneous emission. And the goal is really to look at the FMO complex dynamics with this method. So motivation we have in the group and many others, and probably in this call for over now 10 years since the early experiment 2008, people are looking at the solution of these kind of problems, like for example, how birds finding their magnetic north. Remember, the Earth magnetic field is half Gauss. It's so small that it's really amazing how they correlate their motion with the half Gauss. And in photovoltaic materials, again, you excite the electron in the p-n junction, and you look at the dynamics of this exciton. And the question is, can we run these kind of problems on a quantum computer? And I will focus on the photosynthetic complex, where here we take, like you can think about it as a quantum wire, take the excitation from the sunlight to the antenna, you form an exciton, and the dynamics of the exciton from the antenna to the reaction center. We all in this field say it's about 100% efficiency, and people trying to understand why this is so efficient, what is the role of environment. And people, and on this call, as I mentioned, many did a lot of calculations. There's a lot of excitement, and still people doing experiment to improve the model Hamiltonian for this system. And as I mentioned, our group and many groups really looked at these kind of three problems. And here I will focus on this molecular wire, which once you excite from the sunlight, the antenna to form an exciton, you would like to transfer this exciton to the reaction center. And one simple example that many people looked at this is the FMO complex with 7 sites, where each site you can think about it as a 2-level system. And again, how birds finding their magnetic north. And in photosynthesis, we focus on, can quantum coherence enhance the efficiency of solar cell? And we know in this field, the efficiency is bounded by the Shockley-Quasar limit for a single junction, and the limit said it's about 33% efficiency. That's it, because you have a well-defined 3 mechanism for losing the efficiency, but nobody took into account the quantum coherence. So our argument that quantum coherence can enhance this one and break the Shockley-Quasar limit, we have seen this in theoretical work, but so far no experimental verification that one can break the Shockley-Quasar limit. So for me, I mean, if you look at these 3 problems, they have unified structure. They all start with the sunlight. In photosynthesis, you excite once you absorb the sunlight in the antenna, you excite the electron, you form exciton, you have a transport, you go to the reaction center, and you turn sunlight into chemical energy. For solar cell, we have very similar process. You excite the electron, you form electron hole exciton, and you have a transport current, and you turn sunlight into electrical energy. For the avian complex, the same thing. I mean, they absorb the the photon, they excite the electron, you have transport. And we talk about the radical mechanism. And here there is a chemical reactivity between singlet and triplet. Somehow they are correlated with the Earth magnetic field. And people say we can go from sunlight to direction. So what is the quantum master equation? I mean, we teach this in dynamical classes. You have a system and path. You write the Hamiltonian for the total system as the system for the Hamiltonian for the system. This is A, and B is the path here. And you take interaction between the system and the path. So for the whole system, we can describe the dynamics using the von Neumann equation of motion, because it's the whole system is closed. So the density matrix for the whole system evolve with the computation relation between the Hamiltonian for the whole system and the density matrix for the whole system. But our interest and what we can do experiment on, we're looking at the system, how the system evolve as it interacts with the path. And for that, we take the density matrix of the system and trace the degrees of freedom of the path. So we take the density matrix for the whole system, trace the path, and we're looking at how the density matrix of the system evolve with time. Once you do this one, you end up with the master equation. So this is the master equation. So you look at the dynamics of the system, and you see there is a unitary evolution, which comes from the Hamiltonian, and this is the density matrix. And there you have the rest here, which is what we call the dissipator. So we'll go through the details of this, but this is really telling us about how the system interacts with the environment. And for example, in decoherence, you lose coherence to the environment. So as I mentioned before, the Lindblad approach or the Markov-Born approximation is the simplest one. You said at time t equals 0, there is no correlation between the path and the system, no entanglement, and you can separate the density matrix of the system and the one with the path, assuming the path is at, for example, at the ground state here. And the Hilbert space is the tensor product of the system and the path. So this is now, you look at the density matrix, rho of t for the whole system, you take this unitary dynamics for the whole density matrix of the system and the path. But as I mentioned before, we are interested in the system, so you trace the degrees of freedom with the path. So you can see if you trace it, and now you introduce an orthonormal basis of the environment. So this KB, so you sum over all KB, and you go from here to here by inserting the identity matrix of the complete orthonormal basis of the path. So you see, you sum over all KB, and this is the identity matrix, and this is the adjoint. Now it's clearly you can separate this into two terms. So this is the path basis function U, and this is the path here, and this is the system. So by doing this, now we see what is the Krauss operator. So the Krauss operator is in, somehow you put all the environmental effect in this Krauss operator. And since you work from the basis function of the environment, this one is an operator on the system. And this is the density matrix for initial time t equals 0, and this is the adjoint. So what we call this one is the Krauss operator. And now we can write the master equation as a Krauss map, and you sum over all k, and these are the Krauss operators and the density matrix at 0 time. So since we're dealing with density matrices, this Krauss map should be linear, trace preserving, hermicity preserving, completely positive, and all of these conditions can be met. Let me just move on here. With the what we call normalization condition, that the sum of all the Krauss operator the times the adjoint is the identity. And here I have to stress these operators are non-unitary operators. Okay, as I mentioned before, what we have to do now, we take these Krauss operators and do dilation using this theorem, which originated in the 50s by many mathematicians. And they said that if you have every contraction T in Hilbert space H has a unitary dilation U, or Hilbert space K containing H. So essentially, we're taking this Krauss operator, and we can prove that this is a contraction, which means I can dilate it in larger Hilbert space. And usually when you do one dilation, you double the size of the system. So you can do dilation, and now we turn U into a unitary operator. And we all have seen this one, we that probably call it this, using the theorem, that if A is this or the Krauss operator, you add on the off diagonal element, what we call the defect operator. And now this is a larger matrix in larger Hilbert space, but this is a unitary. And now the goal is to take this matrix and decompose it into sequence of quantum gates and run it on a quantum computer. Well, in practice, we take our density matrix, which is the sum over the probability of finding the system in this basis function, and we flatten this basis function in the vector vi, and the goal is to do the dynamics or the evolution of this vector. But now, once we dilate it, we have a larger matrix. So what we have to do to this vector, we add ancilla zeros here to match the dimension of this vector to the new dimension of this U in larger Hilbert space. So we have to add ancilla qubits into our dynamical calculations. Sorry. So I thought, just like a warm up, I will give a textbook problem, which is the amplitude damping or spontaneous emission. The system is a simple two-level atom, and the path is his electromagnetic field. And you can think about the system as one qubit. The path is another qubit, so U2 qubit problem. And this is the unitary. If the system and the path were in the ground state, nothing happens. You continue the ground state. If you excite the system from the ground state to the first excited state, there is a probability B that the system decay to the ground state, and then as a result, you pick up photon and you excite the path to 1, and here the square root, and this is still, there is 1 minus P probability to stay in the excited state. So this is the simple problem with 2 qubit, 1 qubit for the system and 1 qubit for the path. And now you can construct your Krauss operators. These are very simple operators. They're given by 2 by 2 matrices here, where P is the probability of decaying to the ground state or losing photon. And now it's easy. We can dilate it. It will be 4 by 4 matrices. And we take the gamma, which is the decaying rate. You pick up this a typical one, 10 to the 9 per second, and we do the dynamic from T0 to about 1000 picosecond, and we compose this 4 by 4 matrix into sequence of quantum gates. Oh, sorry. And in average, we have like a 13 to 14 gates representing these 4 by 4 matrices, and this involves the X and the Hadamard and this U3 with the rotational theta here and control NOT gate. And now you can run it on a quantum computer. And for the detail, we put all the couple of simple examples in this scientific report of last year. So now we can do the dynamics, and you look at the results. They, for example, run it on Qiskit, where the solid line is the exact calculation, the dots from the Qiskit simulation, and the IBM real machine with the crosses. And you can see clearly, if you start with 1/3, 2/3, the excited state decay, and you pick up the population in the ground state. So you can do the dynamics and run it on this machine. Now, if you would like to calculate an observable, you have to be very careful. If the observable is you have to make sure it's a positive semi-definite, but we have a well-defined procedure how to turn it into semi-definite operator, and we're using this decomposition, and there is a decomposition we did it here, for example, if you have -2 here, we say how we can use this formalism to decompose it and make it positive semi-definite, and the cost, you have more gates because you have 1 extra qubit for this decomposition. But we can do any observable with this method too. So then we run it with just another complete all the simple example like phase damping. We get the same phase damping, and then gens coming, which is you have an atom interacting with a field, with bosonic field. Again, this simple problem, they are 4x4 matrices and can be done easily and run it on both the simulator and the real machine. So here I'd like to just move to the FMO dynamics, and here we show how to map the Krauss operator or connect the Krauss operator with the Lindblad operator. And this is all done simply in many textbooks. It's very simple. You expand the density matrix from T to delta T, and as a result, you expand also this Krauss operator in delta T, and you go the dynamics to first order in delta T, and you collect the terms. And you can see there's one-to-one mapping between the two problems, and you can turn your Krauss operator into the Lindblad formalism by identifying the Krauss operator with the index K starting from 1, 2, 3 is going to the Lindblad operator K with the delta T here. And for normalization, there is a K here, which is allow us to normalize the Krauss operator. So we have now we know how the Lindblad operators or the Lindblad equation can be transformed into Krauss operators. So now what we did in the dynamics, we said, okay, the density matrix at step time n related to the density matrix at n-1 by this relation. So what we do in the real simulation for this FMO complex, we do iterative process. We start at 0 and then move the steps in, and we did in this simulation 6 time steps in this simulation. So for example, row 1 is related to row 0, row 2 related to row 1, 3 to 2, and so on. So we have iterative process to do the dynamics. So we start running, running the FMO complex. So what is this FMO complex? Is you can think about it as a quantum wire that connects the antenna to the reaction center. This is a 7-site, and we did, and many others also did even 7-site, but you have different paths to go from the antenna to the reaction center. So the simplest approach is to take only the 3 chloroform, this one here, 1, 2, 3, to go to the reaction center or the sink. And when this is so you can write your Hamiltonian in terms of the 4 sites here. You have 3 sites plus the sink and the coupling between them. And these are raising and lowering operators for the system. And these are the coupling between the chloroforms here. So this was run, for 3 sites back by David Mazzotti and his group in 2011, and show that you can capture the dynamics by 3 sites instead of 4 sites. And for us, it's easier really to run it with 3 sites. So we run the dynamics with the steps around 50 femtoseconds. And here we have the 3 sites. And the last one will be going to the sink. And we have 3 dephasing operators here. And we have 3 dissipative operators. Dephasing, you go from 1, 1, 2, 2, 3, 3. And dissipative, you go from excited to the ground state here. Dissipative. And the last one will be the sink. You go from 3 to the sink here. So we have 7 and the normalization. So we have 8 Krauss operators to be simulated on the quantum computer. So my student, Andrew, ran these simulations on CASM and the IBM machine, and we get the exact dynamics by taking 30 data points with 5 runs. So we were able to really capture the whole dynamics that were done on a classical computer. So again, these are the parameters we are chosen from. So it's the parameters for the dynamics were chosen from this earlier paper in 2011 with the 3-site, and you have the sink. Anyway, so the conclusion with this kind of iterative approach one can run it on a classical computer and get the exact dynamics. So now the problem is how many terms, because you do dilation and you do multiplication. So the number of terms really go exponentially with the system size. If you do it six iteration and you have 8 cross operators, so you have 8 to the 6. But what happens if you look at the specific of this problem? It is really, if you look at these matrices, you have only 1 or 2 elements different from zeros. And when you multiply these matrices, you have a lot of zeros. So if you put like a bound on the norm of the matrix, and we took here the bound to be 10 to the minus 2, you can reduce the elements dramatically from large number like this one to 6200 here, 144 to just 800 terms. And this simplifies the calculation. So essentially, one really has to look specifically on this problem and see that these matrices are really, you have 1 or 2 elements different from 0, and the rest is zeros. So you have the sparse nature of these matrices. And for the dynamics of this, if you go complex, we just put our paper in the archive. And this was a collaboration with Katie and Bria at Harvard and David Mazzotti at University of Chicago. And we just, a couple of months ago, 2-3 months, we put it in the archive for all the details of how these calculations were done. So again, this is just a summary. We can do this calculation. And now the question is, how do you go to larger size of these molecular wires? Like, can we also do the dynamic for the 7th side, the original problem? Or can we go to a larger system like the LH2, which is 18 sites? And we have done classical calculation, this one, and it was so difficult for conversion for, you have 2 to the 18, 2 to the 18 by 2 to the 18. And again, I mean, experimentally, they can move, larger, you have 27 and so on. So can we use quantum computer really to start addressing the dimension of these large systems? So the next we're trying to do is the 7th side, and for the 7th side, we need 4 qubits, because you have 7 times 2 with the dilation, and then you have the sync, so it will be like dimension 16. So we think with the 4 qubits, one can simulate the 7th side, and then maybe the next step, one can go with the double excitation, where we have seen in our earlier work that double excitation is really making a difference for the dynamics. But the system becomes larger, we have 56 by 56 dimension, and this becomes a larger system to be simulated. Another approach we are taking is, and we're discussing with the quantum optics group here at Purdue, to see if one can manipulate the 2 unitary matrices directly with the optical setup, instead of decomposing it into sequence of 1 and 2 qubit gates. And we're doing that. If somebody's interested, we put like a review article on how to look at qubits and high-dimensional quantum computing in Frontier Physics last year. And we're doing that because we saw with the experimental group, for example, how you do phase estimation with qubit and qubit space. So there is a promise that one can do the shifting with the optical setup, which can reduce the computational cost. So the last one, I would like to mention the non-Markovian. In the group, we did just Markovian. And then as a follow-up paper was by David and Bria that they put also in the archive after our calculations, that they can do samples of Lindblad trajectories. And from the samples, they can introduce the delay in time or the history of time. Then they claim that they can capture the dynamics with Markovian or memory of the path related to the system. And again, this is the end of it. And again, I would like to give credit to all the students that are doing this hard work here in the group. And thank you for your attention.
Thank you very much. Thanks a lot for the nice talk. So let's give a round of virtual imaginary applause. And okay, then let's get to the questions. Do people have questions right now? If they want to, I'm looking at the Slack channel. Okay. If not, maybe let me start out with one question. So you imagined, so you envision going to larger systems, right? Which is probably
Yes.
the overall goal, right? So
Uh-huh.
if you do that, what are your assumptions on how the Lindblad operators are given to you? Are they going to be sort of given to you as local matrices that sort of overlap, or are you assuming a more general model? The reason why I'm
No.
asking is, okay, sorry, go ahead.
Yeah, no, for example, for non-Markovian, and okay, you have to look at the physics of the system. For example, when you look at this FMO complex, what you have dissipation and you have dephasing. So you have to know the physics of the problem to get these matrices in the Lindblad. So yes, this is somehow has to be given. And once we have this Krauss operator in a matrix form, then we'll continue with the application dilated and go to the quantum simulations. But the first stage, I mean, giving these operators, yeah, they have to be given understanding the physics of the problem. And you can see the beauty of this one. You have, when you look at the dephasing and dissipation, you have two states. So this is why all the matrices are sparse matrices with only one or two elements different from zero. So we were discussing this before. I mean, if you look at the overall, I mean, this looks very complex. But when you zoom in on the physics, it's really, you have very, very simple matrices to be simulated.
I see. Okay. The reason why I was asking, so if you look at sort of thermal dynamics on those systems, like, I don't know,
Yep.
these thermalizing maps, and when you do the Markovian approximations and so forth, they become really, really big non-local matrices because you sort of have to have jump between eigenvectors. Would you envision being able to simulate systems like that as well, or is it really restricted to sort of local dissipators in that sense?
No, I think, no, we can, no, in principle, we can do it also for larger system where, and we looked at the thermal distribution from to add it to the James Coleman model. And no, this is, I mean, you increase the non-zero element in the matrix, but in principle, this can still be decomposed into sequence quantum gates. I mean, the complexity will be much harder because we reduce the terms, for example, from hundreds to only, I mean, it's like was over 100,000 terms into 800 because of the simplicity of these matrices. But in principle, if I have a more complex matrices, I have no problem of decompose it, but it was going to take more resources to decompose it into sequence of quantum gates.
Okay. Anybody else? Other questions? Do people have more questions? So Sabre wants to know, in the case of non-Markovian systems, the path B should keep memory of the interaction with the system. Could you elaborate if all the Krauss approach you introduced can extend to this case?
Yeah, we did not do this one. I mean, this is what I mentioned. Maybe I will hear the show that the last one. This is the work done by David Mazzotti and his group. I mean, they put this one on the archive. We are not involved in this one. But their claim is that they can do an ensemble of Lindblad trajectory. So each Lindblad trajectory, we can do it with our approach. And then their formalism, I mean, you can look at this paper. They claim that they have a way to do ensemble of all Lindblad trajectories and then capture the non-Markovian dynamics. So we have, this is not our work, but this is work by David Mazzotti and Bria. And they just put it 2 months ago, I think, or 1 month ago in the archive.
Okay, cool.
I mean, to start, I mean, this is really a more general question. I mean, how do you do the master equation without doing all this simple like Lindblad or weak coupling? I mean, can we have a strong coupling, or we can start with the kernel where you have a memory there? I mean, yeah, you have to start there, and then the complexity. How do you map it into Krauss operators? But it looks like the average sampling of Lindblad is the easiest one because each trajectory can be done with our approach.
But what is puzzling, if I can extend the question, is that it seems that when you explain that you can extend it to the non-Markovian case, you assume that locally you assume Lindblad representation, which means that it's Markovian. So
it's one thing like that. It's why the ensemble. It's
strange for me.
Yeah, this is what I mentioned before. I mean, their claim that the ensemble of Lindblad trajectories over different lags of time can give you the Lindblad, can give you the Markovian or the non-Markovian dynamics here in this, and they run it for a simple example of James Coming with harmonic oscillator as a path, and they claim they get the exact dynamics when you include the memory. effect.
Okay. Okay, thank you. I will check this paper actually.
Okay, I think with that we're good on time. So let's thank the speaker again, and thanks for all for attending. Thanks a lot. Bye.